getting a little bit nervous, but I'll do my best. So, my name is Tomoki Shibata. I'm from Tufts University in the United States, and my co-authors are Danielle Afergan, Danielle Beste Yuksel, and Professor Scott MacKenzie from York University. And my research advisor at Tufts is Professor Rob Jacob. So today's topic is about text entry, but we have a restriction here. So today's topic in my talk is actually text entry on ultra-small screen, ultra-small touchscreens. So let me begin with my talk by asking this question to you. Do you really think it's possible to type on the ultra-small touchscreen like a smartwatch? So if you have a wristwatch, it's kind of funny to ask, but if you have a wristwatch, please make sure you still have it on you. And in the meantime, I'd like you to see the size of your watch face to answer this question. Good, thank you very much. I saw lots of people check your list, that's great. And I actually asked this question to many, many people so far in informal way. Then interestingly, or maybe not, most of the answer I got from them was something like, well, you know, it will be difficult to directly touch character key on the ultra-small touch screens. I hope all of you kind of agree with that answer. And the possible explanation why it is so difficult to touch tiny character key on the ultra-small touchscreen could be our normal size finger really overlap many, many parts of the user interface. And another possible explanation is that just the size. There exists the incompatibility of the size of tiny user interface element with our human's normal size finger. So this kind of observation is well known nowadays. It's well known as the fat finger problem. Simply saying our human being's normal size finger is too big to directly touch tiny user interface elements. We think this is a real problem because we clearly see that this fat finger problem is limiting human beings to interact with powerful wearable computing device such as smartwatch. So we kind of also know that simple direct touch will easily suffer from this fat finger problem. So the motivation in our research is to design alternative finger input forms to enable human beings to type on the ultra-small touchscreens. So next slide, this slide, let me introduce our solution for addressing fat finger problem. DriftBoard, a panning-based text entry technique using fixed cursor and movable query keyboard. As we can see in this figure, we placed a US 1-cent coin next to our ultra-small keyboard. So now you see how small it is. This is the size of user interface we are dealing with. And the core idea of DriftBoard is that instead of asking you to make a direct tap on the ultra-small space to select a character, we ask you to make a panning to move the movable query keyboard with respect to the fixed cursor point. So the panning is a kind of finger input form. As, for example, if you use your Google map on your cell phone, you probably navigating the map by using panning. That's the thing. And it's probably easier to show the video first how DriftBoard works. So let me play the video first, and I'm going to add some explanation later on. And this is a DriftBoard, and DriftBoard is consists of 3 key components: fixed cursor, movable query keyboard, and interactive area. And then user makes a panning on the surface. Then you can user begin by placing their finger on, finger down, initiating panning, and the finger move continuously translates the position of movable query keyboard. And whenever user releases the finger up from the interactive area, character selection happens. Then, if the fixed cursor acquires nothing, at the time of finger release, no character key is selected. And also, user can begin panning at any part of the interactive area. So user really doesn't need to touch keyboard anymore. So the video was a little bit rushed, but let me add some explanation here. So while designing or prototyping our technique DriftBoard, we made some design choice. We still use a query layout for movable keyboard so that we can expect that the user can still leverage their past experience while interacting with DriftBoard. We also set the size of movable QWERTY keyboard so that each key is reachable from any other key with one panning action. So this is important to mention. Then what I want to say really is that one character can be typed with one panning action, one input action. So another is that we purposely place the fixed cursor on the left side of interactive area for right-handed user, because so that user's finger doesn't really go over on the fixed cursor point. But this is kind of configurable things. For example, if we have a left-handed user, we probably better off of placing fixed cursor on the right side of interactive area. And this is a little bit conceptual view, but DriftBoard is clearly in GUI paradigm, because DriftBoard has a window, DriftBoard has a cursor, DriftBoard has a target. But what we did in this research is that to make panning works as a text entry method is that we flipped the movement strategy of visual elements, meaning that in DriftBoard, cursor acquisition point stays at the same place all the time. In the meantime, target, keyboard moves on the surface. We also believe that our DriftBoard can be the solution for the fat finger problem for two reasons. The first reason is that DriftBoard resolved finger occlusion problem because user can begin the panning at any part of the interactive area so that user really doesn't need to pinpoint the exact pixel on the screen. Plus, we purposely place the fixed cursor point to the left of the interactive area, as I already explained. So finger doesn't really go over the fixed cursor so that user has a clear vision on the place where the most important things happening while user is typing. The second reason is that DriftBoard can resolve finger precision problem because character selection happens only at the time of finger release, so that user can still refine their finger location until they are feeling comfortable to select the character. By having this reason, we believe that our DriftBoard is an efficient means to address fat finger problem. So I feel that now you start thinking this works, DriftBoard works as a text entry method, but next question would be how well it works. So we conducted user study. We utilized a text copy task where participants were asked to transcribe phrases, and we randomly picked the phrase from MacKenzie and Scofish, the word set, which is a representation of English sentences. And the phrase to be transcribed appeared on top of the user interface, and the character the participants typed will be appeared on the middle of user interface. And the bottom part is obviously the keyboard. We also made a 2-point of comparison to evaluate our system. So we picked the two published ultra-small keyboard. Both of them resolve the fat finger problem in unique way. The first comparison was ZoomBoard, which was presented at CHI 2013. And with ZoomBoard, user makes 2 consecutive tap action to select a character. So the idea is that first tap on the interactive area enlarge the keyboard. Second tap executes typing. And another comparison was Swipeboard, which was presented at CHI 2014. And in Swipeboard, user makes a 2 consecutive swipe action to select a character. The idea is that first swipe on the interactive area, select one of the 9 regions, and the second swipe to select the character within the selected region. And I have a video to show how each of techniques works, so please take a look. The first one is obviously ours, DriftBoard. We categorize our technique as a panning based because user makes panning to type a character. And the middle one is ZoomBoard, tapping-based approach. First tap enlarge the keyboard, and second tap execute typing. Okay. The right one is Swipeboard, swiping-based approach. The first swipe selects one of the 9 regions, and second swipe selects the character within that region. Okay, so let me go back to my slide. And we implemented DriftBoard and replicated ZoomBoard and Swipeboard on the watch size touchscreen. The configuration we set was the size. We set the size of interactive area as 28 by 14 millimeter, which was roughly the half of the smallest watch face available at the time of we conducted user study, which was almost 1 year ago. And we utilized within subject design and recruited 10 participants. All of them are right-handed user and native English speaker. As a result, we got 1,455 phrases to analyze. And here is the result. The left chart is showing text entry speed in word per minute, and higher value is better. And right chart shows error rate in percentage, defined it by MSD method, minimum distance string method, and lower value is better. And blue line is for DriftBoard, red line is for ZoomBoard, and orange line is for Swipeboard. So in terms of the fastest typing speed we observed, DriftBoard achieved 9.74 words per minute with 0.6% error rate at 10th block. ZoomBoard achieved 10 words per minute with 1.35% error at 7th block, and Swipeboard achieved 8.52 words per minute with 2.46% error rate at 8th block. And we applied statistical analysis to evaluate our system, and obviously independent variable were input method that we tested, like ZoomBoard, DriftBoard, and Swipeboard. And dependent variable are text entry speed and error rate. We also have other variables like efficiency by keystroke per character and task workload by NASA TLX, but they are not here, so please check our paper for full analysis. And in terms of text entry speed and error rate, ANOVA indicates that the main effect of input method was statistically significant for each dependent variable. And post-hoc analysis shows that there is no significant difference between ZoomBoard and DriftBoard in terms of both speed and error. And there is significant difference between Swipeboard and DriftBoard in terms of both speed and error. What I mentioned was just a comparison to describe performance of DriftBoard, and please check our paper for full analysis. So by having this result, we positive to say the performance of DriftBoard panning-based approach was comparable to ZoomBoard tapping-based and were better than those of Swipeboard swiping-based. Then now people might think that how good 10 words per minute is, or is there any way to improve this text entry performance? I want to say yes. Then we think the most promising way to leverage the language model. By incorporating language model, we can enable system to offer word character prediction and auto error correction. So it definitely helps to improve performance. And if I can concentrate on the DriftBoard, our method, we probably should try to make our system more streamlined of input. What I mean by streamlined of input is that we think DriftBoard works very well with shape writing method. I'm referring to shape writing method with a SHAC2 presented at UIST 2004. By incorporating shape writing method, we believe that we can eliminate potential finger down up method within the word. So in other words, now DriftBoard can type one word per one panning action, not one character per one panning action. So if we have a chance to utilize pressure-sensitive touchscreen, we can potentially replace finger up action with finger press action, so that user can type many character with one panning action without releasing their finger. So this is a takeaway. We think that text entry on ultra-small touchscreen is still challenging. We haven't found a clear dominant solution for it. We introduced DriftBoard, a panning-based text entry technique to enable human beings to type on the ultra-small touchscreens. We hope our work contributes to opening up this nascent design space and eventually to unlock the full potential of powerful wearable computing device. Last question. Do you now think it's possible to type on the ultra-small touchscreen with DriftBoard? I hope to hear a lot of yes from you. Thank you.
Okay, let's take some questions from the audience. Yes. Please say your name and affiliations before asking questions.
Hello, my name is Nikhil Sharma from Google. This is really interesting. I was wondering why you chose QWERTY layout and also the long space bar and the standard layout, or some reasoning for it, considering that people are not going to be tapping but moving. And also if you tried other keyboard layouts. Thank you.
That's a fantastic question. And the reason why we utilize QWERTY layout is that we just wanted to leverage users' past experience. So user is already, we assume that our participants were really already familiar with QWERTY layout, so that user really doesn't need to look up which character is where. So we can, I would say, we really don't need to train user to start using our system. And yeah, so the QWERTY layout is the only one we tested for this research, but having other layout, for example, circular or other layouts has to be checked as a future research.
Any other question?
Thank you for the interesting talk. As you just said, DriftBoard adopted the traditional QWERTY layout, right? So I'm wondering whether the superior performance of DriftBoard in your evaluation actually is caused by the higher familiarity of participants with QWERTY layout than the other two.
Oh, I'm sorry, could you say that again? I'm so sorry.
So the other two baseline text entry methods, I think they are less familiar to the participants in terms of, and the DriftBoard use a QWERTY layout, which everybody is familiar with, right? So I wonder whether the better performance you observed is caused by higher familiarity of participants with QWERTY layout than the other two.
So I think he's asking that the Drift keyboard use a QWERTY layout, right? So that's that one of the contributing factors that you saw the outperformance over the existing technique?
So I think the QWERTY layout is the only one we tested. So as I said, we should test other layouts also. Then I have no idea how we can apply other layouts for the comparison we tested. So having QWERTY layout, the original implementation of two published.
So one thing you may try out is to run a multi-session kind of a longitudinal study to see, over time whether the performance of participants using other two methods may change.
Yeah, maybe we should take it offline because we don't have a time. Sorry for that. All right. Okay, thank you very much. Let's thank Tomoki again.